These two, like,
That really doesn't sound very right. Because it's slowing down as it gets closer. As time passes.
but it increases at first.
This one was like this was hot.
Okay, we're going to take some time to talk about the homework today. So we'll start with my math lab. So I'm going to just scroll through to remind you what the problems were. And you can kind of remember, and then we'll pick maybe 2 or 3 to talk about. So number 1, given the rate functions, determine the accumulation function, match them up. That was number 1. Number 2, given the rate function, answer questions about the accumulation, like max, min, and zeros. Number 3 was the same as that. Just a different, they gave you a different rate function. Number 4, 4, 5, and 6 then were about applications. Given the rate, answer questions about accumulation, given a application rate. So that was the, number 6 was the water leaking out of the tank. Number 5 was the cost. And number 4 was number of bacteria. Okay, so suggestions for which ones we should talk about. Yeah?
Which are one of the maximum minimum ones?
Yeah, the previous class wanted to talk about number 2. So number 1 was the matching. How did that go? So given the rate,
Good.
this is really important because it's really sees if you understand the idea of accumulation from rate. So that's, go back and review that if you need to. Hey Joe, could you do me a favor and shut that door? And maybe also tell me your name in the blue shirt.
Gabriel?
Gabriel, can you shut that door back there? Thank you so much. Okay, so what we've got here is the rate function. So this is the rate function, and they're asking about zeros of the accumulation function. Remember, so I said anytime it's at area, just call it accumulation. And that's the same accumulation function that we've been doing, right? 0 to x, rate dt, okay? And so they give us the rate function. So notice that they haven't added a constant to this accumulation function. So if they're adding for zeros, there's kind of an obvious 0 right off the bat. Where is the accumulation going to be 0?
0.
Yeah, right when we start. Okay, so that's going to be one of our zeros. Oh, unfortunately, I've already answered this. So pay no attention to the man behind the curtain. Okay. All right, so here we go. So the accumulation is 0 because no bits have been added or taken away yet. Okay, and we're not starting with some initial amount. So without starting with an initial amount, our accumulation will start at 0. Okay. So then what happens? So let's just talk about this first part here. From, say, 0 to 1.5, about. So from 0 to 1.5, based on this rate, what's happening to the accumulation? So from 0 to 1.5, talk to me about the accumulation in this interval of x. Calvin?
The accumulation is decreasing.
Accumulation is decreasing. Would you agree with that? So if we started at 0, and we started with actually not adding bits, but we're doing what? Through there, taking away bits, right? So you got to imagine it. We start at 0 and we start receding, right? We're taking away bits. What's the accumulation going to be through there? Negative, right? So what's gonna happen is do that here. So we'll start at 0, and then up to this point, 1.3, we're going to be taking away bits because the rate is negative. Now, what's going to happen, say, through this part right here? What's going to happen to our accumulation? Are we going to add bits on, or are we going to take bits away? We're going to add bits on. So starting here, now we're going to add bits on. So what's the accumulation function going to do? It's going to increase. So we took a bunch of bits away, and we were in negative territory for the accumulation. Well, then we started adding bits back on. So logically, there's going to come a point when the amount of bits that we took away will be the same as, there'll come a point where these new bits that we're adding will be the same as the bits we took away before. So about where will that occur? So 1, 2, 3, 4, or 5. About where do you expect the bits added here will be the same as the bits we took away? Yeah, something. Do you see that something right about there? Just eyeballing it. This much accumulation taken away is going to be about the same as this much added back in. And so we took away, and then we started adding them back in, and then right about there was where the net effect was to be back where we started in terms of 0 accumulation. Does it make sense? So we can approximate that to be. So we knew we had 0, and we can approximate that to be 3.5. What happens after that? So now we're here. What are we doing now? Adding more bits, taking them away?
Adding.
Adding. What about here? Adding or taking away bits?
Adding.
They're saying adding. Is it right? We're still adding bits because the rate is? We're going to keep adding bits all the way to there. So from there to there, what will the accumulation function do? From there to there. It'll keep going up. It'll keep going up. We're adding bits that whole way because the rate is positive. Okay, but then when we get here, now what's happening to the accumulation? Yeah, so here we'll be taking away bits again. So the question is, all this that we added on, will this amount that we take away get our accumulation back to 0 again? It's not enough. All this, so we're adding bits all through here. We were at 0 there, and so starting from where the accumulation is the same as when we started, and now all through there we're adding bits, and then we're taking away a little, but not enough to get back down to 0. So the only time we would predict the accumulation would be 0 would be at the beginning, and right there at 3.5. Ben, question?
The one you have, the answer was 3.5.
Uh-huh.
I don't know if anybody else had it, but mine was 3.3.
Was this? Yeah, it's approximation. So just because we're estimating, they give you actually a range that will get it correct.
Okay, so it's actually divided into folds.
No, to get it correct, you just have to get it close enough. There's a whole. I could have put 3.42. I could have put 3.31.
So it accepts a range.
What's that?
So it accepts a range because the other ones wouldn't. A lot of the other.
Because you're estimating here. You're just having to eyeball it. So they can't really fairly say you have to get exactly right. So they allow you anything probably from 3.3 maybe to 3.6. As long as you get into that range, your guess is good enough. Does that make sense?
Mm-hmm.
Yeah. Other questions about finding the zeros of the accumulation? Okay, what about local max and min? Well, we've done the hard work here. So where is there a maximum minimum of the accumulation? Where's the first one? 3.5, right there?
No, sorry, 1.5.
Why is there a minimum at this point? So that corresponds to this right here. Why is there a minimum accumulation at that point? Well,
because the rate changes from negative to positive.
Okay, and so when the rate is negative, what's happening to the accumulation? Losing bits. And as soon as the rate changes to positive, then what happens? Start adding bits. So that's the turning point from decreasing accumulation to increasing. So the first guess would be around 1.5. Where else is there a max or a min? Is there another one? Here? Nope. So why is that a maximum accumulation? Somebody new over here. Yeah, as well.
It changes the sign from positive to negative.
What changes sign?
Does the bits start changing from being positive, it's taken away?
And how do you know that? How do you know it's right there? It's changing from adding bits to taking away bits.
Because in the first graph it shows it in the positive part gets smaller, and then once it hits the x-axis it starts to go in.
Right. So your rate, when your rate is positive, we're adding bits. But then as soon as the rate turns negative, that's going to be the turning point where we start taking away bits. So this looks like about 8.5. So 1.5 and 8.5. Questions on this problem? Is it better? Really, so that's important. Really test your knowledge of how accumulation comes from rate, right? Other questions on this? Okay, how about of the last 4, 5, and 6? So 4 was the bacteria, 5 was the cost, and 6 was the water leaking out of the tank. Any requests? 4 is which one?
Oh, well, we can do this. We can do this one. Can we go over 5? That's fine.
Okay, let's maybe get consensus. 4, 5, or 6? 5? 4? 4? I'm hearing 4s and 5. You want to do 4 and 5? All right, so 4. Okay, so what I told you was that this, here's what I put. So what I told you in part A was it wouldn't count for credit. If you got it wrong, it didn't count against you. Why? Because we haven't really talked about, actually we're going to start kind of talking about this today. So what did I put in, or what would you put in? What is the number of cells, as far as we know, after T days? This we should be able to do. So what's an expression that will calculate the number of cells after T days? Ben?
Integral starting at 0, ending at t,
Okay.
and then 40 e to that power.
Mine was 0.3662. Okay, can I put T here? Yeah, I got to do something different than T. Something that represents this quantity, but allowing it to change from 0 to T so we can accumulate the bits. So I'll use A. Okay, I'll use A. It's fine. Normally we use X and then T in here, but as long as these are different, it's fine. Okay, does this give me the number of cells after T days? Yes or no? And if no, what does this give me something else? Somebody new. Connor?
Don't you have to add 200 to it?
Okay, so he wants to add 200 to it. So now it gives the number of cells. What if we didn't add the 200, just what we had before? What would it mean? Somebody new. Is it Anand? What would, if I took the 200 off, just had the integral, what would that represent? Ashlyn?
It would be how many cells you have. Would you like to change yourself from 0 to 9?
The change in cells. Adra likes it. Is that what you're going to say, Calvin? Yeah, so if we take the 200 off, then what does our accumulation start at? 0. That will start at 0, and it'll calculate the change in the bacteria population. So if we add on the initial amount, then we get the actual population after T days. Okay, so in terms of part A, this is what you'd be responsible for right now. Right now, you should be able to come up with that. Okay, so after 8 days, how many cells are present? What are we going to do? How are we going to get the number of cells present after 8 days? Set up our accumulation function. AT equals sum of R times A plus J minus 1 delta X plus left. So what we're going to do? What are we going to do? We want the number of cells after 8 days. Jennifer?
You just plug in 8 into the first one.
Will that give us the right thing if we plug in 8 to this function? What does this function give us? Does it give us the number of cells after t days? It's exactly what it gives us, right? It's our accumulation function. We added the 200, gives us the number of cells, so if we want it after 8 days, we just plug in 8. So we can just do this here, 200 plus. Once you get in the habit of using graphing calculator as just the way you use a handheld calculator, you'll never go back. It's so much more convenient. Okay, so 200 plus, control I, 0 to what? 8 of 40 e to the 0.3662 is what I had. Can I use x here?
Yes.
I'll use x just because the problem comes when we're doing the function. If you're just plugging in a value, any variable is fine. So x is fine. The problem is if you're doing the accumulation function, these cannot match. Those cannot match. So it's showing 2135.57. So I'm guessing, so after 8 days, we would have 2,135 cells. Does it want the decimal? Nope. Got it. Questions on number 4? Does it help? What if we wanted the increase in cells from 8 to 13 days? How would we get the increase in the number of cells from 8 to 13 days? Ben?
N of 13 minus N of 8.
Okay, good. That would be...
Or you could put in into your integral, instead of 0 and 8, 8 and 13.
So there are 2 ways to represent that. Good. If we want to calculate this here, I didn't set up the n function, so I'm just going to go with the second thing he said. What did I say, 8 to 13? So if we start accumulating at 8 and finish at 13 of that rate function, this will be the increase in the number of cells. That also can be expressed as n of 13 minus n of 8. So the total accumulation at 13 days minus the total accumulation at 8 days. So that thing right there equals n of 13 minus n of 8. Question?
Yeah, so instead of like trying to do integrals on MyMathLab, you expect us to always do it on graphing calculator?
Yeah, so you're going to... no, so this particular question was asking for something that we haven't done yet. But in terms of computing accumulation, it won't compute things for you. Well, I guess it will if you put in expressions for your answers. But yeah, use graphing calculator to do as much as you can.
Okay.
Yeah. Okay, and so then, good on number 4? Okay, number 5. So what do we got? We got, this is called the marginal cost function, and I told you in the tip, marginal cost is the cost for the next unit, which is virtually the same as what? What is that? The cost for the next unit. That's rate. So this is rate of change of cost. So this is our rate function. And we want to know the additional cost from when you started at 100 units and ended at 150 units. So in all the stuff that we're doing, how can we apply what we're doing to get, we've got the rate, how fast the cost is changing. We want to know how much cost we have, starting at 100 units, additional cost, starting at 100 units, ending at 150. So what tools do we have to do that? Kim?
So you created an integral function with 4,000 minus, let's see what yours says, but mine had 0.6x.
Yep, 2000, okay.
And then times dx, and it should start at 0 and end at x. Is what I had, but it came up like 4,000 off.
Okay, so if we want the additional cost, when we increase from, starting from 100 units to 150 units.
And then you take c of 150 minus c.
Okay, so you built the function. So that's fine. If we use x here, though, we don't want to use x here. So we can use something else. T. Fine. And you built this as the cost functions, all right? And you wanted to do, so now to get the additional cost from 100 to 150, you said? Yep. Total cost for 150 units minus total cost for 100 units. Absolutely, that will work. Is there another way? Is there another way to represent this additional cost, starting at 100 units and going up to 150? Later.
100 on the bottom of the integral and put down on top of the integral.
Yeah, so we can do this. We can start accumulating at 100, finish accumulating at 150, accumulating little bits, rate times change, rate times change. So here's, what are we doing? Again, review. That's one little bit, right? And what does this mean? Add them up all the little bits, starting at 100, ending at 150. So I could build this function in Graphing Calculator and then put a line C150 minus C100, or I can just do that in Graphing Calculator, which is what I'll do the second. Control I, 100 to 150. What's my rate function? 2000 minus 0.6 x is fine. So the additional number of units, 96,250. Where is it? Back there. 96250. Got it. Okay. How about the written portion of the homework? Can we come to consensus here on one to talk about? Nomination? Yes, sir.
We'll go over number 3.
All right, he wants number 3. Other suggestion? Yeah. 4? 4? We got a 3 and a 4. 4. 3. Okay, so we're between 3. So all in favor of 3? All in favor of 4? About the same. I'll try to talk about them both quickly. Oh, okay, 4 is pretty quick. All right, so 3, meteor falling. So the speed. So what kind of function is this? If this is the speed x seconds after entering the atmosphere, what do we got? Rate. It's everything we've done so far this semester, we start with rate. How fast something is changing. How fast something is changing. So this is going to be our, we call this rate, Rx. Find an integral whose graph shows the number of miles the meteor has traveled at every moment during the first 20 seconds. Okay, so we want an integral So there. Okay, so what integral can we set up for the first 20 seconds? Well, it'll be the integral from 0 to x of the rate. So I'll change the x to t now. Okay, is this the number of miles it's traveled, or is this the height above the Earth? Is this the number of miles traveled or the height above the Earth in the first x seconds? What do you think, Jimin?
I have a quick question.
Okay.
On the rate, it says miles per hour.
Yeah, right.
But then the question asked in seconds.
Excellent.
Should we convert it?
Do we need to convert it? So this is a miles per hour, and then it's asking for number of seconds. So how, if this is then, this is going to be miles if, it's going to be a number of miles based on what? Based on 0 and x and t being hours. So if we want those to be seconds, so if it goes this far in an hour, how far is it going to go in a second? Is it going to be 3,600 times that, or that divided by 3,600? It's going to go a lot shorter distance in a second. That's one way to think about this. It's going to go a lot shorter distance. We don't want to multiply by 3,600. We want to divide. So we can. So yes, we can. If we divide that rate by 3,600, now we're talking about miles per second. All right. So don't furiously change your homework. Listen. This the most important thing is understand it. Okay. Understand. Don't worry about, getting 2 more points on your homework. Okay? Does it make sense now? So now we just converted all this t and the x into seconds from hours because now this is a miles per second rate. Okay? Okay? How? And so again, is this the height above the ground or is this distance traveled? Yeah, because at 0, it's going to give us 0, right? And we know that's not the height at the time 0. So this is distance traveled. So how far did it travel in the first 10 seconds? What will we do? Plug in 10 for x. Plug in 10 for x. Okay? How far did it travel from 15 to 20? So plug in 10 for x and put this expression in graphing calculator. It'll just give you the answer just like that, right? 15 to 20 seconds. 15 to 20. Start accumulating at 15, end at 20. Put that into graphing calculator, boom, it'll give you the answer. Okay, so then how many seconds after reaching the Earth's atmosphere did the meteor crash into the Earth? So you have to have the distance. You have to have the distance. So there are different layers of the atmosphere, but kind of an accepted breakpoint of atmosphere and space is 62 miles. Is an accepted breakpoint. Let's see if I have this up here. Here. So what I did was I put in my rate function. There's my rate function that we said. Is that the same one? 15,000 minus 13.8? Where's the 0.407? Here? Why is that different? Doesn't make sense. All right, well, anyway. So the general idea here, I don't want to get into I'll have to figure this out later. But the general idea is we got the rate function, and I'm going to set up the accumulation function right here. I'm going to graph my accumulation function, accumulation of distance. And when I do that, I'm looking for, so points on the accumulation are time in seconds and distance traveled. So if we're saying that the top of the atmosphere, or the break point for the Earth's atmosphere to outer space is 62 miles, then I want a distance traveled of 62 miles. So I get as close as I can there, which is right about there. And then I can zoom in and get a little closer. Here's 62.03. And then the x-coordinate then is the time that it takes to travel that far. We're accumulating distance, right? This is the accumulation of distance. So it takes that long, 16.18, to accumulate 62 miles of distance. Okay, any questions? So I know there was a number discrepancy. Don't want to take class time to get into that, but the idea is the important thing. Okay, hand up your homework.
We're going to do number 4.
I'm going to show you number 4 while you hand it up. So number 4, it just said that your rate function was sine, and we want to build the accumulation function for very small values of x. So you take your standard accumulation function, and you make the rate sine, and you make delta x dx. So this is our rate function, and we want very small values of delta x. So we're going to apply the rate there, and apply the rate function there, sine, instead of r of it. We know exactly what that r is. It's a sine of that value. And then everywhere there's a delta x, it's dx. Is this... So talk to me. Is this kind of what you were thinking? Something like this? Is this... Or something totally different? Or talk to me. So I want to hear your thoughts about this problem. Yeah.
I kind of, like, I explained it. I didn't really understand the question. I wrote out in words what the integral means.
Okay. Yeah, so here's the key. As we would write it as an approximate accumulation function. So how did we write an approximate accumulation function? We built that long form, right? So that's, yeah, Kim.
I also thought that was a little bit vague when I wrote out the meaning, but I'm not sure you might want that as well, so
You put both.
you might want to.
Yeah. So, the full meaning expression. Yeah, so the key is expression as we would write it as an approximate accumulation function. So that was the cue. I mean, it's okay if you wrote out a paragraph, but writing it out as an approximate accumulation function, that was the long form that we built. So that was the idea of this problem. Other questions? Okay, so I posted this full solution to the written, and I'll try to get caught up on the old ones, getting solutions posted. So for Friday, you won't have, we're not going to have homework. You can start studying for your test next Thursday. Okay, so we got a test a week from tomorrow. Start going back and I've got this homework solution posted. I'm also going to post the solutions to all 3 quizzes that we've had since Exam 1. So that's a really helpful way to study also. And then, like I said, I'll be working little by little to get all your homework solutions up for your studying. But start studying soon, and so you can have some time to do that rather than working on homework for Friday.
Can you post blank quizzes too, so we
Yeah, I
can
will.
test them?
I will. I'll post them together. I'll post a blank version and the solution version.
Thank you.
Yeah. Other questions? Yeah.
On the test, how do you allow to use graphing calculator?
No, so yes, a handheld calculator, but it will be written in such a way that you don't need graphing calculator. But I encourage you to use it. It's just too hard logistically with laptops down there. You can't do it. So, but whenever you're working in this class, I encourage you to use graphing calculator as much as possible. It's just we just can't do it on the exams in the testing center. Yeah. Other questions? Okay. Let's see. Okay. I've got a expression here. And I'm going to graph it. And I'm going to pick a point. And this point is, so here's the expression. That I'm graphing, and here's a point on that graph, and so I want you to, this is 2.33 and 0.73 is the coordinates of that point right there. So I want you to talk to the person next to you and interpret what's going on here. So interpret the meaning of this point given that I've graphed this expression. Go. So what's the meaning of that point given the expression that I have graphed?
Yeah, you just want to do that as time.
Say that again.
Find somebody to talk to. Everybody talk to somebody.
So, change from what it was in 0 to what it is now. It's pretty much at 2.3.
Okay, so let's hear somebody new, someone's interpretation of this. How about Lauren? What's an interpretation of these values, this point here, 2.33, 0.73?
Well, at 2.53, if we were to plug that in for t in single time, the total accumulation would be 0.73.
Okay, so she said at 2.3, the total accumulation is 0.73. So this idea, the total accumulation is 0.73. Say more about that. What does that mean? Yeah, Katie.
It means that for every x value up to 2.33, all of those added together, all of the rate values added together
Okay.
equals 0.73.
Okay, so it's the sum of rates. Is that right? The sum of the rates is 0.73.
The sum of the change of the
Sum of the change of the rates. LJ, what do you think? So first of all, is this a sum of something?
I think what we were discussing is that it's kind of the change of something from your initial 0. If that makes
So
sense.
it's like a total change starting from 0.
Yeah.
Okay? Total change starting from 0. Is it the sum of something? And if it is, the sum of what? Nick?
Would it be the summation of all the delta y's?
Summation of all the delta y's. And a delta y is the same as rates. How do we get delta y from rate? How do we get delta y from rate? You Tom. Don't know. So
It's the rate times delta x.
yeah, so it's the sum of bits, right? The bits are rate times change. Rate times change. So it's not a sum of rates, but it's a sum of of bits, and we get the bits by taking rate times change. So how did it accumulate to 0.73? What was the journey of the accumulation where then we reached 0.73? Okay, so mathematically, how did we get to 0.73? Saskia?
How did you get to 0?
Yeah, so we've said that this is the accumulation of a bits of change starting from 0 and arriving at 0.73. So what was the journey like? How did we get there?
You went up, then down.
So, okay.
I mean, like.
And so talk to me about bits. If we went up, then down, talk to me about bits. Richard.
Starting from 0 and going all the way to 2.53, we took the values of cosine times both values of 0 to 2.53 and added them together.
Okay. And what happened along the way to arrive at 0.73? Nathan.
So, like, all the bits accumulated were increasing up until like 1.5, and then they started like decreasing after
The
that.
rate increased.
Yeah.
Okay. So here, what are we doing? Are we adding? Oh, Kim, go ahead.
Oh, I was just gonna add that the rate would actually be positive until it reaches that maximum, and then the rate would be under the y-axis.
Okay, so I want to hold off on rate for a little bit. I just want to focus on how did we accumulate to arrive to 0.73. We are going to talk about rate for sure. That's what's that?
I said we added all the little bits together.
We kept adding bits together. We kept adding on little bits until we reached 0.73. Utah.
We add all the bits together from 0 to 1.5 each, then we start subtracting all the bits from 1.5 to 2.63.
Yeah, what was the accumulation, say, around here? Around here, what was our total accumulation? When we were at about 1.7. We reached the accumulation of 1, right? And then after that, the total accumulation went down. So did we keep adding on bits until we reached 0.73?
I mean, we added negative bits.
Okay, that's true, yeah. So when we think of that, so it's like taking away. So for a while, we added bits until we got up to 1, and then we started taking away bits. We started taking away bits of change, and then we arrived at 0.73. So when we were adding, so tell me where we're adding bits. Am I adding bits here? 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 No. So right here, about 1.7. We're truly adding bits. We're making the quantity larger by adding little bits. So now what about the rate there? So what could you say about the rate in that interval where we're adding bits? Increasing. Positive. So both are for sure. So for sure, if we're adding bits, the rate is the rate increasing? The accumulation is increasing. The accumulation is increasing, but the rate is just positive, right? So the rate is positive. And so how will that graph? If the rate is positive, what will we see in the rate function? No, what will we see in the rate function if the rate is positive? How will that show up?
Above the x-axis.
Right. Above the horizontal axis. Okay? Now, what about in this part right here? What are we doing? What's happening to the accumulation? Okay, R is less than 0. What's happening to the accumulation? It's decreasing. So bits are, yeah, you can think of it as taking away, or what Saskia said, adding negative bits. Okay? So, I'll say taking away. All right, so then that's for the rate of change is less than 0. If the rate is less than 0, then it's like we're receding, right? We're receding in little bits. We're ebbing away in little bits. Okay? What about the rate function then? Can we say if the rate's less than 0? Below x-axis, right? Okay, what about down here? So what about from here to here? Tell me about the rate. First of all, tell me about the accumulation function. What's happening in the accumulation from here to here? Joe?
You're losing all the stuff that you gained. Well, you got to 0, so let's say you have like a bunch of money, and now you're going to be negative.
Okay, so yeah, so in this part, what happened to our accumulation? We started at 0, went up to 1, and now back to 0. So we added all these bits, and then we just took them all away again. So now we're back to where we started in terms of accumulation. So are we adding bits again here?
No.
Taking away bits, but if we're taking away bits here and we're taking away bits here, how is this part different than this? What's different about this than it will?
Because prior our accumulation had gone up and then it went back to its point of 0, but now we're taking away even more than we had to begin with, so it's like we have negative bits.
Excellent, yeah, so in this part, yeah, we're taking away bits, but we're still in the black, right? So we're still in positive territory compared to where we started. If we continue to take away bits, it's like we're going into debt now. We have less than what we started with as we keep taking away. So we're still, the rate is still negative, we're still reducing bits, it's just now we've crossed into having less than what we started with. So, what is the rate function? Let's graph the rate function and compare. What is the rate function? If we take an integral of a function, that function is, what kind of function is that? That's the rate. Does it match? So the first thing we talked about was like 0 to 1.7. So here's 0 to 1.7. Does it agree with what we said? Why? What's going on?
Because you are still accumulating, but you're accumulating less quickly.
Okay. But as much as we said was, our rate is positive and we expect it to be above the x-axis. So we're accumulating, we're adding bits. And then what happens? Actually, all the way from there to about 4.7 or 4.8 for that whole interval, we said that we'll be taking away bits. So our accumulation decreases. How is that shown over here? Rate is less than 0, below the axis. So taking away bits this whole time. Okay, so that's somewhat review. This is, our cosine is our rate. So now look at the accumulation function for a rate function that's cosine. Do you recognize anything from your past experience in math? What does it look like? Yeah.
Just right.
Okay, shifted. So it's the same graph shifted right. Will. Okay, so it looks like it might be the sine function. How can we test it? Yeah, graph, and that same graph, let's graph y equals sine x. So if I turn off, here this is sine x, and now I'll turn it back, and this is our accumulation function. As far as we can tell, these are the same. These are the same. So what we're seeing here is what we call this form of the accumulation function here, we call open form. Open form means we're writing the accumulation function as an integral of the rate function. Okay? And we spent a month paying our dues to be able to do that. Okay? We spent a month paying our dues to be able to just, in one step, write an exact accumulation function. This thing of integral is a very powerful tool for us. We can just write it down. When you express the accumulation function this way, we call it open form. But now we're seeing that there's a common kind of function that is our accumulation function for cosine, which is sine. So when we write an accumulation function just not as an integral, but as just a common function, we call that closed form. Okay, so remember the rocket basketball. What was our rate function for the rocket basketball? 2t. So I'm going to graph 2t over here, or 2x. Okay, so here's rocket basketball. And a point on this graph represented, quickly, x value was what?
Rate. No,
X value? Time in seconds.
Y is rate.
Y is the rate, or the velocity, at that time. And we built a step function, and we built a piecewise accumulation function, and we did all that work, but we're going to just go straight to the exact accumulation function. So this is our open form of the height, the accumulation of height of the basketball racket. Observations? Will?
Kind of looks like half of a parabola.
Okay. Which parabola?
X squared.
Is it x squared? How do we test?
Type it in.
Type it in. Does it appear to be x squared? Okay, so here's, what is this called here? This is an open form of the accumulation function of height, the accumulation of height. What it looks like, and we haven't proven it, but what it sure looks like here is that for that 2t function could also be written much more easily in closed form as y equals x squared for x greater than 0. So the question is, does every open form have a closed form?
Yes.
Does every open form have a closed form? You're saying yes. Someone say no?
I say no.
Okay, so here's just 1 minute. This is kind of cool. No, I didn't want that. All right, so here's sine of x cubed. As a rate function. If I put that in, I can create this accumulation function as the integral of sine of x cubed. And this is what I get. Because what happens? It's spending less and less time, positive, then negative rate. Positive rate, but it's spending less and less time. So the accumulation for these shrinking intervals where it's positive or negative means less of a change in accumulation. So it's moving up and down ever so quickly as those intervals shrink. Anyway, does it have an accumulation function? Yes. Does it have an open form? Or closed form? No closed form. So, every rate function has an accumulation function, but not all of them have a closed form, meaning a nice function that we can write without an integral. Okay, start studying for your test. Oh, and then Friday there will be no recitation. You get to start your fall break early.
Getting you a new shirt. The recitation, I don't getting you a cooler one.